Hello. All right. A couple notes on calculus notation and approximations. I'm not going to review all of calculus in this lecture, but I will highlight some important bits that we're going to need probably sooner rather than later. There'll be some other stuff that will be reviewed kind of as we need it. But this is also to remind that there are some expectations that at this point you have mastered derivatives, the chain rule, basic integration, U substitution, techniques of integration, that those things should be pretty comfortable at this point. Things that are more complicated like div, grad, and curl, I think we actually won't need all of those later on in the semester, but we'll review those. Line integrals, things like that, we will review when we need them. And a lot of that vector Calc 3 stuff comes up more in E&M than this course, at least in the stuff we will cover. But we'll review once we need it. But I do want to make do a couple examples and talk about things that are perhaps not as emphasized as much in the mathematics courses that can be helpful in a physics context. Of course, there's just the machinery. Mathematics machinery you can do by just doing examples. And if you need, and some of the examples I do on these videos, since they're intended to be kind of concise videos, some of the examples might jump in sophistication rather quickly. If you find the examples too complicated, find easier examples to do first, right? Good rule of thumb, always solve simpler problems first if you are having a hard time with a particular problem that you're trying to solve. Find something that's similar-ish and solve that instead, and then good chance that it's going to excite some sort of intuition or some sort of memory that's going to help you on the more challenging problem. Well, let's check this one. Perhaps I have the trajectory of a particle r of t that goes as 4 times 1 minus e to the negative t over 2 all over t. And I get asked questions like, what is its derivative? What is the limit as time goes to infinity? What is the limit at t equals 0? Notice there's that 1 over t, so I can't necessarily just plug in 0 in this case. Of course, we could always start with a graph. If you're analyzing functions, always good to start with a graph if you can do it. And if you were to graph this on a calculator or something, you would see that it looks something kind of like this. Maybe this is a couple seconds, and it seems to plateau here at the value 2. Not plateau, but it seems to reach the value of 2 as t goes to 0. All right, it seems like it's getting smaller and smaller and smaller, and I can look at that function and think, okay, well that makes sense to me, because as t gets really big, the exponential is going to die off. That's a good thing to always have in mind. E to the minus t, right, is always going to kill off as t gets really big. And then there's that, so that goes to 0, so the numerator looks like it's going to a constant, and then the denominator is getting bigger and bigger and bigger, so I expect this entire thing probably is going to go to 0 at the end of the day. So limit as t goes to infinity of this function, I expect to be 0 in that case. Now the derivative allows me to introduce this dot notation. So derivative dot notation that most books in classical mechanics use. And this is really used for time derivatives. The derivative d by dt, so I don't have to bother writing that every single time. I replace that with just being a single dot over the function. So dr by dt is instead just written as r dot. If I see r dot, I know that I take r, I take its derivative with respect to time, that's r dot. R double dot, same sort of ideas. The second derivative with respect to time. The derivative operator is applied twice in that case. So I'm going to use the dot notation moving forward, and as does your books. So r dot, the derivative of r with respect to time. If I look at this function, it looks like that is the derivative d by dt of 4 I'll move the t upstairs. 1 minus e to the minus t over 2. And then this is just plug and chug. Looks like it's product rule plus chain rule. I have no time for the product rule, or sorry, the quotient rule. Quotient rule is really just the product rule and the chain rule combined, right? So here I've made it into something that's not a fraction. So then if I do the product rule, looks like the derivative of the first part, 1 minus e to the minus t over 2, plus 4t to the minus 1 times the derivative of the second part. Looks like it's going to be negative e over 2, and chain rule negative 1/2 at the end of the day. Let's see, some things simplify. Got a 2 here, got a 4 here, that becomes a 2. These negatives cancel, and I think that's it. So then if I simplify, let's see, so there's some e to the minus t over 2's flying around. I could get a common denominator by making it 1 over t to the second power. So this looks like it stays the same. And then it looks like I'm going to put a t, and I'm going to multiply by the top and the bottom by a t. So it looks like then this becomes t e to the minus 2 all over 2. Oh, sorry, nope, that 2 went away. It became times 2 over t squared. And then it looks like if I simplify and do some factoring, it looks like it's 2 kind of t plus 2 e to the minus t over 2. If I lump the exponentials together, there's a minus 4 left over, all over t squared. So if any part of that seemed magical or foreign, these are good things to review. Product rules, chain rules, when you have combinations of complicated functions. So there, okay, that's the derivative. And now the question, let's go back to the function. The limit question, as t goes to 0, if I look at the expression, well, the denominator looks like it's going to 0, but if I think about it, so is the numerator. Looks like it's becoming 0 over 0. In that case, actually, I just realized you could also do a L'Hopital, calculation in order to figure out the derivative as well. That would actually probably be easier in this case. But I came up with this example because this limiting question of as t goes to 0 is very similar to a question that comes up a lot, in that it's asking about the behavior of a function when there's an expression or a variable that is very, very small. In this case, t is getting exceptionally tiny. And I'm asking myself, how does this expression behave itself when t is exceptionally small? This comes up a lot. Either you're, in this case, looking at the value of a variable when it is itself tiny, or you might have to be dealing with, say, perturbations, where I might be asking if I have, some quantity, some calculation I've made, maybe it's the period of a pendulum, and I could ask what happens to the period of the pendulum as I make the pendulum a tiny bit larger, or have the bob be a tiny bit more massive. I could get a complicated expression, but more often than not, when you have these small changes or small perturbations to your original expression, usually you can simplify the expression and get something that's a lot more easy to manipulate and builds a lot more intuition compared to just plugging and chugging the original expression. And so when you are dealing with perturbations, or small quantities, Taylor series are helpful in this case. Taylor series approximations, rather, can be very helpful. And remember, what's the idea behind a Taylor series? The idea of a Taylor series is that you're taking some expression and you're replacing it with its polynomial equivalent. You're turning something that is not a polynomial, presumably into a polynomial, which can be a real boon because derivatives, integrals of polynomials, right? You can do those in your sleep. But what's nice with the Taylor series approximation is not only are you turning into a polynomial, but when you're dealing with a very, very tiny quantity, you can usually also truncate the Taylor series and only keep a couple terms without any major loss of accuracy. So let's remind ourselves kind of the original expression. F of t can be written as a polynomial about some central point t naught plus, and then there's the Taylor series terms, right? As n goes to 1 to infinity, 1 over n factorial, the nth derivative of that function evaluated at t naught. So that's just a number, and then, oops, not x, then t minus t naught. There's the polynomial component to higher and higher powers of n. And again, this is useful in our context when, in particular, t minus t naught to the nth power is much, much less than 1. Or really, I could say that when just t minus t naught is much, much less than 1. Because if that's a small quantity, as I raise a small quantity to higher and higher powers, they get even smaller and smaller and smaller. Right? 10 to the minus 6, I raise it to the second power, that's 10 to the minus 12. Raise it to the third power, it's 10 to the minus 18. These things are dropping off exceptionally rapidly. Such that, assuming that the derivatives, or the things out front, in front of these terms, are kind of well behaved, that they're just kind of typical values, they're not getting wildly bigger or wildly smaller either, that you could probably, you can get away with truncating the series after a couple terms without any major loss of accuracy. Because even though there's infinite numbers of terms, all the terms after the second or third term are so absurdly small that why bother keeping them around? And this is similarly useful when t naught is 0. In that case, you're just saying that t is very, very small. All right, so you're looking at some quantity that itself is exceptionally tiny. So then, for example, e to the t, if I write that as a Taylor series about t equals 0, e to the 0 is 1, and there's plus all the derivative terms of 1 over n factorial. E to the t, the derivative is it itself, so all the derivatives are just e to the t, but I evaluate them all at 0, and they're all just 1, so all the derivatives are 1, and then it's times t to the nth power, and n gets bigger and bigger and bigger. So this becomes 1 plus t plus 1 over 2 t squared plus 1 over 6 t cubed, dot, dot, dot. Goes on and on and on. Infinite number of terms. But again, when t is exceptionally small, again, let t be 10 to the minus 6, then t squared is 10 to the minus 12, t cubed is 10 to the minus 18. If I want to know how much e to the t deviates from unity, which is what you get when you just plug in 0, but I know t is very small but non-zero, this is well approximated by then just 1 plus t, the first two terms. Right? It's not exactly 1, but it's 1 plus that tiny little thing. And then all the other terms have such higher powers of t that we just don't even bother because they're so much smaller than these two leading terms. Right? Sometimes you don't even care about the first order perturbation. Right? Just if I plug in 0, e to the t is just 1. Right? That's the first term. But then if I let t be small but non-zero, it deviates from 1 by the second term. And that's kind of the leading order approximation. So the Taylor series for kind of the typical functions are good to internalize. So good to internalize, e to the x, I'll use x in this case because I'm trying to be general, is about 1 plus x. The sine functions, cosine of x, when x is very small. Well, I know cosine of 0 is 1, so I know it's going to be 1. but then the perturbation on top of that is x squared plus over 2. Sine of x, I know sine of 0 is 0, so I expect there not to be a constant term out front. So it turns out the leading term is x, and then if you have an additional term, it's x cubed over 6. And then there's the binomial approximation, when you have 1 plus x to some power. P could be an integer, could be positive or negative, it doesn't have to be an integer even. It could be any number, it could be a real number. But 1 plus a small number raised to some power, a good one to remember is that this is 1 plus p times x. And of course, there are additional terms for all of these. So you can make sure, right, you can calculate what these additional terms are if necessary. Sometimes you have to. I'll say something about that in a second. All right, so then 4 over t, 1 minus e to the t over 2. I could ask myself then, okay, what 4 over t, fine, then I have the 1 minus e to the negative t over 2. I'm going to replace that e to the negative t over 2 with its Taylor series approximation, 4 over t, 1 minus, and then I know that this is then going to be, if I look up in my cheat sheet, e to the x is 1 plus x, so this looks like it's going to be 1 minus t over 2 in that case. In this case, x is negative t over 2. And again, there are more terms, but I'm only going to keep the first one and see how well we do. And then you can see what happens. The 1's cancel, and it looks like this becomes then t over 2 plus higher order terms. The t's cancel, and it looks like this is 2 plus higher order terms. So it looks like as t goes to 0, this entire thing goes to 2. And again, you could double check that with L'Hopital's rule. Now in this case, I only used one additional term. You could ask, how do I know when to stop? How do I know whether or not one additional term is enough? Maybe I need 2 additional terms, for example. And I guess my answer there is that it takes practice to see. Like, you can always add more terms into the Taylor series approximation, right? If you're worried that you're not keeping enough terms, you could always add some more in, and eventually, once you've added enough terms, all the additional terms that you add in are going to result in expressions that have some positive power of t that are going to go to 0 as t goes to 0. Let me show you kind of what I mean by that. Like 4 over t, 1 minus e to the minus t over 2. Let me approximate that. But now let me keep one additional term. Maybe I was concerned that one term was not enough. So I have 1 minus t over 2. But then I'm going to keep an additional term as well. So then I'm going to add in plus x squared over 2. So then this is going to become, so then this is t over 2 all squared, and then there's that 1 over 2 factorial up front. Dot, dot, dot. So here I've kept one additional term. Really, it's minus t over 2, but again, it's going to be squared away anyway. So then 4 over t, let's say then it's going to be 1 minus 1 plus t over 2. Then it looks like it's going to be minus t squared over 2 times 2 times 2, 8. That's higher order terms. So then it looks like it's going to simplify to the 1's cancel. And I can divide through by a t. So then it looks like it's going to be 4, 1 over 2 minus t over 8. Higher order terms. Or that's going to be 2 minus t over 2 plus higher order terms. So again, I get the same leading term in this case, the 2, but then notice the new term that's added in, because I decided to keep another term in the Taylor series, included something that went as some positive power of t. So again, as t goes to 0, this then just becomes 2. I don't have to worry about that there's some behavior I've accidentally removed. in that case. So Taylor series can be very helpful in making these sorts of approximations. All right, let's see, new page. Then what's happening? Then the binomial one is also very helpful and comes up in a lot of different contexts. Let me just give a quick example of it. Suppose you're standing on the surface of the Earth, and I could ask myself, I know that there's a gravitational force pulling down on me from my feet, a distance of the radius of the Earth from me, from the center of the Earth rather. And that is going to be different than the gravitational force felt on my head, which is near the surface of the Earth, but a little bit higher than my feet, where it's assumed that h is much, much less than the radius of the Earth. So there is a different acceleration that I feel at my head compared to at my feet. Rather than just saying it's 9.8 meters per second squared, really there is a difference between those two locations. And I gotta ask myself, how does it differ between the two? So I could say, of course, the force at my head is going to be g times the mass of the Earth times, take a proton that's on my head, and then it's going to be divided by the radius of the Earth plus my height squared. Is going to be the force at my head. And that's different from the force at my feet, where I would just plug in h equals 0. And you could then calculate that there is a difference between the two. But with a Taylor series approximation, I can actually come up with an expression for exactly what that difference is, in a form that is much easier to look at and reason out versus the difference of these two kind of mixed ratios. So I might first notice that if I want to use a Taylor series approximation, like the ones on the previous page, I need to have a quantity that's assumed to be very, very small. Here we know that h is much, much smaller than r, but h itself might not necessarily be a small number, right? 6 feet compared to 4,000 miles, which is the radius of the Earth. Relatively, it's very small, but 6 feet itself is not necessarily a very tiny number. But I can make it a small number by factoring out the r squared. So I had r plus h all squared, and I'm essentially going to yank out an r from the expression, and it has to go through that square, so then this becomes 1 plus h over r, and that's all being squared. Pause and convince yourself that that's true. I'm kind of anti-factoring it, or I guess I am factoring, right? Rather than multiplying things through, I'm kind of ripping things out through, but it's going through an exponential. Now this h over r, this is a tiny number. So I have, again, 1 plus a very tiny number. Something that then a Taylor series approximation I can use as a way to simplify this expression. And I'm going to use the binomial expression, where I had 1 plus x to the p is about 1 plus p times x. So in this case, it looks like x is being played by h over r, and then p in this case looks like it's being played by the exponent -2. Not 2, -2, because it's in the denominator. So then this force looks like it is going to simplify to gm little m over r squared 1 minus 2 h over r. Or if I factor that out, or multiply that through, rather, looks like it's gm over r squared, and then minus 2 gm h over r cubed. And again, assuming that h is much, much less than r, this is a perfectly valid, great approximation to the expression I started with, gmm over r plus h all squared. And why this, I think, is more useful is because you can stare at this and see, well, the force, let me just recopy it, the force at my head looks like it is like the force at my head is the same as the force at my feet, but then there's this slight change here. So this term here, it's kind of nice because it's showing you kind of the delta F, how the force has changed in going from my feet to my head. And if I'm a static object, or I'm trying to be a static object, that relative force is what's trying to stretch myself out, right? My feet are being pulled towards the earth more than my head. So relative to my head, my feet are trying to be pulled away from my head. This is what's called spaghettification. That's a technical term. There's a Wikipedia page, you can look it up. Usually those are used for effects like this that happen near black holes, where this delta F could be extreme. Because near black holes, capital M tends to be very big, while capital R tends to be very small. So you can get very large forces. And then this also, when you combine it with the fact that the Earth and the Moon orbit each other, or orbit their common center of mass, can also be used to explain tides, of why we have tides on the surface of the Earth. And you can look up things like the tidal force expression, and you'll notice that it looks more or less exactly like what I wrote down here as delta F. And again, their derivation is coming from the fact that they're looking at motion relative to the surface of the Earth compared to, say, a little bit above the surface of the Earth, or in the case of tides, looking at the motion at the center of the Earth relative to motion at the surface of the Earth, which that distance itself is much smaller than, say, the distance between the Earth and the Moon, or something like that. So these sorts of expressions can be very, very helpful. So reminding ourselves about Taylor series, which always comes at the end of the semester when everyone's burnt out and no one thinks, like, oh, who cares? Taylor series actually are probably one of the more important things to take away from Calculus 2. All right, let me make a final point about just calculus notation in general. Yes, there's the machinery of calculus. We just did some examples. But we also want to be able to read calculus and mathematical expressions and know that there's a story that they're trying to tell. Right? So if I say the position of a particle is r sub t, right? I can then translate that with that not only with mathematical certainty, but with physical interpretation, that I can then say the velocity is dr by dt. And of course, I can write down, what a derivative is. But I also know that velocity is telling me how the position is changing as a function of time, right? This expression, dr over dt, those have units, of course, associated with it. The r is position over time, which is time, position over time. And that this can be defined as, right, looking at slopes, or looking at the position at some little time a little bit ahead of t, comparing that to the position at t equals t, and that's all divided by this small amount of time. And as I make that smaller and smaller and smaller, this then represents a derivative at a point, which we in physics can interpret that as the velocity or rate of change at that point in time. Right, and then so this is sometimes written as kind of delta r over delta t, or you can think of it as rise over run, you can think of it as a fraction, and we will be okay considering derivatives as fractions in this course. Mathematicians might scoff at that, but thankfully nature is generally well behaved enough that we can get away with this. So again, by looking at just the definition of a derivative, we can see that as it's a change in position over a change in time, right? There is a physical connection to these variables. All right, so if I write v is delta r over delta t, right, I can interpret that is the same thing as saying that a little bit of change in position is equal to my velocity times a little bit of change in time. And if you want to be more exact, since this is not a calculus expression, right, I might say the average velocity, right? The change in my position is whatever my average velocity is within that time increment times the change in time. In the calculus limit, where I let these delta t's get smaller and smaller and smaller, I can replace that with differential notation. So this differential notation, right, sometimes I think people get intimidated by this, but it's saying the exact same thing. A small change in position is equal to my velocity times a small change in time. That's all it says, right? If the lowercase d's confuse you, right, just imagine them as as deltas, right? Interpret it that way. In the calculus limit, though, of course, we're going to say that, right, this is assuming that these delta t's, right, a tiny, small change in t multiplied by your current velocity results in what? Results in a small change in position. This ultimately, this gives us what? This gives us, if I wanted to write down a mathematical expression, this gives us not r at t, but r at t plus dt, maybe, in that case. I've taken my position, I've updated it to get a new position. And again, calculus-wise, you can think of it as following tangent lines, and if t is sufficiently small, the tangent lines will always hug the curve, even if the curve itself is changing shape over larger periods of time. Usual things you've been taught before. Another thing to remember, now let's go to the other avenue of calculus, which is the integral, is that the differentials here, the dr, the dt, are telling you what variables are acting as the independent variables in an expression when you're integrating. So it's also worth getting comfortable knowing the following and being comfortable with this, with the notation of the following. That when I say delta r, which I could define as kind of r final minus r initial, that is an exact definition of the integral of dr when I go from r naught to r final. This is an exact, actually let me make it red, an exact definition here. All right, those two things are, all those things are the same. Of course, they're connected by an equal sign. What you're integrating over, in this case, is r. You're integrating over r, which then, of course, is why the limits are themselves values of r, in this case, r initial and r final. Now this is the same as, we said that dr is the same as v as a function of t times dt. So this is the same as the integral of v times dt. But now, what are we integrating over? We're not integrating over r. We're integrating over t. So the assumption is that I better be able to write everything as a function of t before I integrate, or be able to justify that other things are not functions of time and can be held as constants. Also, that means my limits have to be appropriate. In this case, the limits are not r naught and r final, but they might be t naught and t final. The times that are associated with whenever your position is r naught, and whenever you're in t final is whenever your position is at r final. All right, so let's not be sloppy about kind of the notation here. The limits have to change in that case, and the limits have to agree with the variable that you're integrating over, the independent variable in this case being t on the right-hand side, or that first integral, the independent variable is r, you're integrating over r. So that, again, the goal is that if there was something in that integral expression, to write everything as a function of r first, then do the integral. Which is okay, even if you think r itself is a function of t for the left-hand integral. if you can write everything as a function of r, you can integrate away. On the right-hand side, you have to write everything as a function of t first before you do the integral. So this comes up, for example, when you do kind of separable differential equations, kind of the one kind of differential equation you see before taking a course on differential equations. So let's suppose I have the following. So let's I have a differential equation where I say the derivative r over t, or dr over dt, is r times t, and I'm also told that r at t equals 0 is equal to 1, my initial condition. This is an example of a separable differential equation. Again, differential equations are just, essentially it's algebra, but you're throwing in calculus in turn of all. Or algebra, you want to, like, say, solve for x. Differential equations, you still might want to solve for x, but it's a function of time. So there might be derivatives and integrals involved as well. What makes it separable is that you can separate the variables on each side of the equal sign. So again, in this case, treating the derivative as a fraction, divided by dt equals r times t. I want r as a function of t. First thing I can notice is that I can get all the r's to one side by dividing by r, and I can get all the t's to the other side by multiplying by dt. Again, treating the derivative as a ratio of differentials. Now everything on the left-hand side is only a function of r, which itself is a function of t, but that's okay. And then the right-hand side is only a bunch of things that are written as functions of time or are just the variable t itself. So then I can integrate both sides. But now I have to ask myself kind of what I expect my limits of integration to be. Now, if you're more comfortable integrating indefinite integrals, which then give you constants of integration, that's all well and good. I prefer, if I can do definite integrals, I'm going to do definite integrals. So I know I'm going from, say, I know when t equals 0, right? Again, remember this is t equals 0, that r at that same point in time, r better equal 1 in that case. Remember, the left integral is integrating over r, so my limits better be two r values. The right integral is integrating over t, those two limits better be t values. I'm working in my initial condition as a limit here, right? When t equals 0, that's the right integral, r equals 1, that's the left integral. And then I'm going out to some general value at some later time t. And again, I'm just kind of making it super general, my upper limit. Again, if you prefer to not have limits and do constants of integration, fine. I like to avoid constants of integration and just work in my initial conditions as part of the limits on the integral. So in that case then, if I evaluate the left integral, 1 over r, I know how to integrate that. That's just a natural log. And then when I evaluate, it looks like it's going to be r over t divided by 1. And then that's going to be equal to the right integral. I can integrate a polynomial. That looks like it's going to be t squared over 2, and minus 0 squared over 2. And then I can solve for r as a function of t. Looks like it's going to be e to the t squared over, oh dear. Well, that's unfortunate. We're so close to the end, too. Sigh. R sub t is e to the t squared over 2 as a result. Really, it's 1 times that. once I undo the logarithm. And that is my solution to this differential equation, which I was able to do by first separating it and integrating each side based on its own independent variable. All right, good things to practice. We'll see a lot of that in the near future. So good things that we'll review as well in class.